Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to the homework session. Now, this week we have discussed potentiometric sensors. And in the beginning, of course, the potentiometric sensors look very simple. The biomolecules which have certain amount of charge, be it a DNA or a protein, they land on the transistor surface or potentiometric sensor surface, changes the potential, and you measure the changes in the current, for example, in the MOSFET, or the change in the voltage for other types of potentiometric sensors. But we soon found out that life is a little bit more complicated than that, partly because of this sort of the dual role of salt. And the salt, of course, was necessary, otherwise the biomolecules will not bind. I have told several times now. And that's also true for antibody and protein. And then there was, but at the same time, the salt essentially took away a significant amount of charge or potential away from the biomolecules, and the MOSFET didn't have much left, giving the logarithmic dependence, as I explained before. So salt was one. The other one was the pH. You know, I mentioned that you could say that, okay, I'm going to be very careful and will not have any pH in the solution. Well, you cannot have that, because water, by definition, has a potential of hydrogen, that's the pH, of 7, which is about 10 to the power 7 moles. They are ionized automatically. And the salt and the pH sort of made things complicated. But we analyzed it very simply, as you saw. And then we had a set of discussions, or a series of discussions on the ways to beat the sensitivity limit. So what I'd like to do in this homework is to sort of amplify certain points a little bit more. Now, the number of homeworks in this set there are quite a few homeworks, and if you go through them systematically, you know, some of them less difficult, some of them more difficult, and then there are this BiosensorLab based simulation. If you go through them systematically, actually you should have a very clear understanding about potentiometric sensors, right? So let me walk you through some of the solutions, which I think I didn't cover in the original lectures that much. I wanted to point out a few things about it. In problem 3.1, I asked you to see whether you can solve this following problem. Assume you have a nanosphere sensor that has a certain amount of charge. Now, this could be a protein, for example, in the salt solution. But let's consider that you have a little sphere and a certain amount of charge is sitting on top of it. So the biomolecules have landed on the spherical sensor surface. And the total amount of charge that you have on the sensor surface, or the spherical sensor surface, is Q. The important point I wanted you to see was that this potential that goes into the solution drops very, very rapidly, exponentially rapidly. So the interaction is very short range. That is, the electrostatic field doesn't keep going. If you had a sphere in empty space, the electric field would keep going and it will gradually decrease as 1 over r. But here, the important point is that it decreases much, much faster. And I wanted to show you how that comes about. If you know how to do the 3D, of course, you'll be able to do the 2D and 1D. So let's see how it works. So by the way, why we are so interested? This short range, because what happens, assume that you have a spherical sensors and all the red molecules are sort of the biomolecules that have covered the surface, and it had a certain amount of charge. And we want to know that how does the potential decay away from this spherical sensor. Now the important point is, what we are going to show that the potential is very strong, very close by. So when the molecules, other molecules come in, salt molecules come in, it attracts them very quickly, very short distance away from the sphere. But if you go a little bit away, you know, look at this sort of isolated atom. The isolated atom even wouldn't know that there is a sensor sitting here. So this strong local interaction is something that I wanted to emphasize in this homework. All right. So the basic idea is that we have a certain amount of charge sitting on the spherical sensor, red spherical sensors, immersed in a salt. And of course, if this is a positive charge, the chlorine is a salt. So sodium chloride, for example, chlorine is negative, and the chlorine atoms will come close by and the sodium atoms will be pushed away. So therefore, there will be a small region where there will be more negative charge than the positive charge in the solution, so that this positive charge in the sensor is fully compensated within a distance LD, and you may remember this D stands for Debye, within this very short distance. So let's see how that solution gives you this particular potential profile. Now I have already solved this type of problem in the class, so therefore we'll just copy, but I want to emphasize where you have to make a modification. Now when you solve this type of problem in the presence of salt and charges, we said that we have to solve something called a Poisson equation. And Poisson equation, you have the gradient squared psi has to do with the double layer charges, with how many sodium atoms you have, and so n minus is whatever number of chlorine atoms you have at a given location R. And we saw that if you have a boundary condition that at this point close to the surface, remember it's a planar sensor, this surface, the potential is psi naught, then far out, of course, the effect of this charge will completely be screened out by the salt. And so therefore far out, nobody would know that there was a positive charge here, positive blue charge here. So the potential at x equals infinity will be 0, because at that point there is no effect of this charge. Now I already discussed that if you know the potential psi, the electron, the chlorine density would go up exponentially, and the sodium ion density will go down exponentially depending on the potential. So what we did, if you remember from the lecture, that we inserted these two things, and e to the power plus x and e to the power minus x, the difference of that became sine hyperbolic. Now one assumption we made was that when psi is very small, if the amount of charge is very small, psi is very small, in that case, I can make an assumption, I can make an approximation, expand the sine hyperbolic in the first order, and essentially write the whole thing as psi divided by LD squared, and LD squared had this complicated expression. You can see it's not very complicated. This is this constant divided by the other constant associated with psi when I expand it to the first order. All right. And then, of course, we solved this first order differential equation to get the solution, to the final solution. And we did see that the potential drops very, very fast away from the sensor surface, exponentially fast from the sensor surface. Okay, so this is easy. Let's see what do you need to do if we were thinking about in 3D. Remember, it's a spherical sensor, not a planar sensor. So if you were paying attention in your college calculus courses, then you might remember that the gradient square in 3D goes as 1 over r and r phi, second derivative with respect to r. It is no longer just second derivative of psi divided by dx squared, not like. It is slightly more complicated in spherical coordinate. But of course, the right-hand side depends only on every point. So therefore, the right-hand side will not change. But the left-hand side would change a little bit. Now, we have to solve this equation, this differential equation, subjected to boundary condition, just like before. If you are far out, the charge has already been screened by the salt, and so therefore the potential will be 0. But the important thing is that at any radius A, the Gauss's law says that the electric field at this point is simply 4 pi epsilon A squared. A is the radius. And since the electric field is the negative gradient of the potential, so therefore now I have both a boundary condition. This is second order equation. I need two boundary conditions. So this is one boundary condition and this is the second boundary condition. Things are fully specified. And the way then one would solve this equation, that this is the full solution. This is a trial solution. You can try it out. So one thing you can see that solves in general the differential equation in the cylindrical coordinate, except when r is equal to infinity, you see the potential has to be 0. Now this term at r equals infinity will decay, but this term will blow up. This first term, because when you put r equals infinity, exponential of infinity, this term will blow up. Of course, the solution cannot be physical in that case. So therefore, we must have a1 equal to 0. So which is good. That means this first term will drop out. Now, how do I get the a2? Well, in order to get the a2, I'll have to use the second boundary condition. Take a derivative and equate it to the total charge from the last slide. And if you solve that, you will get an expression for A2. This is how it works. You see, if you take a derivative of the equation, there will be a psi here when you take a derivative with respect to r, and d psi dr multiplied by r, that's on the one side. And then from this side, if you take a derivative, you will pick up a 1 over LD. This psi, then you can pull to the other side because you already know that expression. And once you have done that, you will see that at r equals a, that is why I want to evaluate the gradient, at r equals a, then correspondingly will lead to this particular expression. And the bottom line here is that the constant a2, therefore, will have this. These are all sets of constants. You know, a is the size of the molecule. And correspondingly, you have an expression for A2 that you can plug it back in the original solution. Now, if you do that, then that gives you the full solution. So the bottom line is, you see, it's good to have some practice in solving this type of Poisson equation in different configuration, because one of the things, as I said, the salt screening is very important in potentiometric sensors. And so this is one example. Why don't you try the cylindrical sensors and see whether you can calculate out this type of response in that case also. Okay. One thing you see, if the size of the spherical sensor was very, very small, in that case, A would go to 0. And when A goes to 0, of course, this will go to 0, it will give me 1, and it will have e to the power r over LD. And when r goes to 0, very close by, not too much salt around, in that case, you can see Q divided by 4 pi epsilon r. That will be sort of the charge associated, a potential associated with the point charge, something that you learn in college physics anyway. So the only thing that salt did was to add an exponential term. Other than that, everything is exactly the same as you have seen in your previous courses. So there's nothing surprising about how this thing works. Okay. So the bottom line is that this short range interaction is very important for life in general, because anytime you have charge, you want it to locally interact very strongly with the neighbors, bind things with the neighbors properly. but a little bit away, the effect of this charge, it should not interfere with other things. So therefore, biomolecules in the solution, salt really plays a very important role. It not only screens away, screening away is a bad thing for potentiometric sensors, granted. But you see, screening away also keeps neighbors fully separated so that they can go on with their own life in biology. Every protein can do their thing, a neighbor can do their thing, and if they are about 1 or 2 nanometers away, they will not know even that the others is present. So it's as if they are in their own world. So this reason, this exponential decay is the reason which allows them to stay in their separate world, although they are physically in the same box. The other thing is a notion of Debye length versus Bjerrum length, and I will explain what that is. So this was problem 3.3. Now, in this particular case, the idea was that Bjerrum length is a distance LB, at which the potential becomes KT over Q. What is KT over Q? KT is the thermal fluctuation in the environment that you have. So you see, if you have 2 molecules like this, and if the potential begins to decay in between, the point where it becomes KT over Q, you see, if you try to go a little bit farther out, then the bond strength is smaller than the thermal strength. It will break the bond, right? And if you are closer than that, then the bond stays fine. So one of the consequences of the screening is this definition that how far can the 2 bonds be apart before they break apart. So therefore, I have to equate this potential for the distance r equals LB, at which it will become KT over Q. Now you can see that this equation would be very difficult to solve, right? This is a nonlinear equation. I know KT over Q, 25 millielectron volts in room temperature. But I have a LB here. By the way, LD depends on the salt concentration. You can calculate. But I have a LB on the exponential, and I have a LB sitting on the denominator. So therefore, only iterative solution is appropriate. In the 0th order, let's assume that LV is very small and very close to A. You know, it's a very small value. Let's assume that, and then we will see how it works. And so then what will happen, that LB minus A will be approximately equal to 0, right? Because I'm looking very close to the surface. This will give me 1. And then this is also in the order of 1. Let's assume that. So then my life is simple. I have only a LB here equals to KT over Q. And then I can get a value for LB. LB is the distance over which the potential has decayed to KT over Q. And you can see, you can easily calculate this. The interesting thing is that while LB is about 56 nanometers in air, why? Because in air, you have epsilon, epsilon relative dielectric constant is 1. So therefore, it's 56 nanometers. This goes a long distance. But in water, you see, epsilon r is 78. And if you have 78, in that case, it is only 7 angstrom. So by the time you have traveled about 7 angstrom away from the charge, because of the straining and because of the salt concentration and the water polarization and dielectric constant, the potential has decayed to a value which is just a KT over Q. That's why 2 DNA molecules are 1.1 nanometer apart, because if they were apart a little bit farther, you could not sort of have any interaction. This screening would have completely killed it, right? So that's why they are a certain distance apart, and this calculation essentially allows you to see that what is the binding distance between 2 charges in salt solution. Now, of course, you may complain that this is not an exact calculation. True. All you have to do now is, if you wanted to make this thing self-consistent, you have to take, let's say, 0.71 nanometer, put it in here, and then recalculate. And then once you recalculate, then you can go back and forth and refine it. By the time you are done, you will see the value doesn't change significantly. Here also, you can do the recalculation, put it in a computer or do recalculate on your own, but the value will not change significantly. In this case, it will. In this case, because of the salt screening in air, but not in water. So therefore, this approximation is quite reasonable. All right. Now, we discussed in one lecture about the origin of the charge in a biomolecule. Remember, I said, why is DNA negatively charged? By now you know, right? That DNA is negatively charged because its backbone, it's an acid, first of all, right? And deoxynucleic acid. And so therefore, it has this phosphorus backbone, phosphoric acid residues. That's where the charge comes from. Now, this problem really talks about pH changes and the implications, because this is something even in many researchers essentially incorrectly report, capture of biomolecules where all they have done is that they have changed the pH and changed the surface concentration of positive and negative charges, or change the charge of the receptor molecule, incorrectly thinking a target molecule has come. Let me explain. I think you will understand better if I show you the picture. You remember that there are this target molecule, right? This is a DNA. This is a polymer DNA. Okay. And then I had this target. This is receptors, and the target molecule was supposed to come in and bind to it, and there was salt around, and the point was that initially, let's say you had 3 charges. Later on, you will have 6 charges, and from this difference, the sensor would know that a target molecule has been sort of bound together. Now, what I want to tell you next is that even if you didn't have this target molecule, this blue target molecule, you simply had changes in the pH in the solution, the green molecule, the charge of the green molecule itself will change. And as a result, somebody sitting in here on the sensor side and not paying attention what is happening to pH will incorrectly think that the blue molecule has come. Blue molecule may not even be there. Simply because of the change in the pH, the green molecule's charge will change. So you will have a false positive. You will say that there is some disease, but there is actually none. It's just noise. So let me show you how that happens. You may remember this particular plot, that as a function of pH going from 2 to all the way to 14 or 0 to 14, the charges of the DNA essentially kept changing. The green one is when it was not charged at all. At high pH, a low pH value means very high proton concentration. Essentially, there is no dissociation. That's the green charge. And the red one, when it has one charge, a single charge. So every backbone, every base pair has one electronic charge. And the blue one has 2 electronic charges. And then this final piece, here is the final piece, 3 electronic charges per base pair. So let's see. So if you start with 2, so somebody has changed the pH from 2 to 8. So these are the 2 places. So now look at 2. At 2, on the green curve, you will see about 60% of the charges, there was 60% of the DNA base pairs will be uncharged, right? That's what this is. This is green curve. So assume you have 100 base pair in the DNA. 60 of them are uncharged and 40 of them are singly charged. So therefore, what is the total charge for a 100 base pair? The total charge will be at pH 2 will be 40 Q. That will be the total charge. On the other hand, if you change the pH to 8, right? We are all talking about just the receptor molecule now. There's no target molecule. Now, if you are here, then what you will see that at pH equals 8, about 90% of them are essentially singly charged. 90% of them are doubly charged. So 90 multiplied by 2 is 180. And about 5% are singly charged. That's on this rate curve. What is the total charge? 180 plus 5, 185 Q. So simply by changing the pH from 2 to 8, my charge has gone from, the receptor charge has gone from 40 Q to 185 Q. So a person who is not careful will assume as if a biomolecule has been captured with a total charge of 145 Q. Now, granted that this is an extreme example, I just wanted to make a point. The thing is that even if you change pH from 7 to 8, there will be significant amount of change in the charge of the receptor itself. And unless you are careful, you will actually just report that parasitic disturbance in the fluid that has got nothing to do with the target biomolecule. So this is the reason why I gave this particular homework problem. All right. Now, calculating the protein charge is a little bit more complicated. So, but this is sort of very important because why is more complicated? Because remember, it's a polymer. But unlike DNA, which has all the same charges, all negative, it could be 0, 1, 2, and 3 for DNA. The issue with protein is that the protein has both positive and negative charges, and 4 of them are positive, 3 of them are negative, and correspondingly, things are a little bit more complicated. But the good news is that there are these calculators, and I have given step-by-step instruction. It is sort of very important that once you do it once you have gone through this exercise, you will never have any trouble. Any molecule that you have in the protein data bank, this protein data bank have thousands and thousands of proteins. Any protein that you're interested in most likely is there. And so lots of information. So it's a very good idea. This PDB is a protein data bank. You go there, work through the problem, and you will have a very good understanding for any protein what the charges would be. The formula that gets evaluated in the back, I discussed in the class, is something like this. Depending on the amino acid which are negative plus amino acid which are positive, you add them up, and correspondingly that gives you the total Q. And for every amino acid, the rate constants are all given. But the point I want to make, that's those things you can look at the solution. These things are all there. The point I wanted to make was this very important point where the charge becomes charge of the solution at a given pH completely disappears. What it means is that the protein has lots of amino acid. Some of them become negative, some of them become positive, but when you combine them all, total charge is 0. And if the total charge is 0, potentiometric sensor cannot see it. So therefore, anytime you want to design a potentiometric sensor, first thing you have to, especially for protein, first thing you have to do is to do this calculation. Go to the protein data bank, go through the steps, plot this curve. And once you know the pH value where the charge disappears, the point of 0 charge, your first goal would be to move away at least 1 pH value away from that point, either on the positive side or on the negative side. You cannot stay here. You will not see anything. But at the same time, you have to be very careful. Don't go too far out in here, because if you go too far out in here, yeah, you have a lot of charges, but the structure of the protein will change, right? Because the positive and negative residues will not fold properly. And therefore, when you're trying to catch it hook it by this antibody, it will not fit properly. And so therefore, you want to stay close by. This was the purpose of this homework. Hopefully, you have been able to work through this problem. All right. Finally, I'll show you just one more example about how to beat the screening limit. And one approach we said was this SUPERNERNST sensor. So I gave you an example. For example, aluminum gallium nitride has a mobility of 2000, oxide thickness of 45, width of 1 micrometer, and there is a corresponding silicon nanowire. So this is the sensor. And the silicon nanowire, on the other hand, has a mobility of 100, oxide thickness of, let's say, 15 nanometer, and width of 50 nanometer. And I want to know what type of amplification will I get, right? What type of amplification? So this is the silicon nitride one, the wide one. And this is the silicon nanowire one, the skinny one, the narrow one. And we always put the salt or the solution in the wide one. That's very important to remember. If you put it here, your amplification will go in the other side. It will actually go, instead of amplifying, it will sort of degrade the signal. So you always put the solution on the big one. That's the thing to remember. And what I said that, the change in the current for the big one and the change in the current for the small one, if you add them together, the current should be 0. I mean, that is how this detection scheme works. And the final formula was something like that. The final gain is whatever is the pH change on this sensor will be amplified by this ratio of the capacitance and ratio of the mobility, width and all. So the homework is related to that problem. So let's see. So all we have to do is to just put this value. What is the mobility? Mu1 is, I already had added there 2000, and mu2, 100 for silicon. W1 and W2, it was, 1 micron, which is 1000 nanometer, and 50 nanometers. So you get another ratio there. Length is about the same. So with channel length, we'll not worry about it. Channel length here is the same. And here we said the VDS, they are connected to the common drain. So those are the same. And oxide capacitance, you have to be a little careful because oxide is inversely proportional to, or capacitance is inversely proportional to the oxide thickness. So when you are doing COX1, it will be 1 over 15. And when you are doing COX2, then this would be the corresponding 1 over whatever the thickness was. So you put it in, you get about 1/3. Put this whole thing in, look at this value. This is 8 volt per pH. What was the normal limit if it were alone? The normal would have been 59 millivolt per pH. So you have a tremendous gain in terms of pH sensitivity. So this is something that can be very helpful if you wanted to have a super sensitive design. Finally, there was a BiosensorLab homework example. There's only one reason. This is very nicely laid out and the solution has everything, so you should be able to take a look. I just wanted to point out one thing about this solution. So this is pH, x-axis is pH, and the y-axis is surface potential. How much potential has changed when you have changed the pH a little bit for a given sensor. Now the important thing is that as you are going from, let's say, 2 to 8, remember the example that we talked about? The pH response is not linear. It begins to saturate towards the end. So most of the time I'm saying 59 millivolt per pH or 8 volt per pH, assuming this response is linear. Now, of course, if the response is not linear, saying something like 59 millivolt per pH is sensitivity makes no sense because that's just the slope. And the slope will change depending on where you are. So you have to say at what pH was that slope. So the important thing is not to rely on that slope number all the time, but rather do the full calculation. BiosensorLab has the ability to do the full simulation. And so therefore, in that case, let's say you have decided to build your sensor at this point. This local slope will be your pH sensitivity. If you have decided to build some in here, then that will be your sensitivity. So the full pH response is very important. Don't always rely on this differential slope because that really doesn't give you the full insight about how the sensor works, right? It's a nonlinear device. charge is coming in, pH is changing the surface concentration, lots of equations playing its role. So expecting that at the end there will be one number describing everything is not realistic, right? But a tool like BiosensorLab can do the calculation for you and you'll be in good shape. Okay, so this ends lecture. There's potentiometric sensors, homework associated with it. Now, just want to make sure that this is one of the most important sensor that have been around. So make sure you study this part very well, because we will come back to this again towards the end when we talk about genome sequencers, right? Genome sequencers are potentiometric based sensors. So if you understand this clearly, all this pH response and all, then you will see that those lectures would be crystal clear to you. You will have no problem in understanding at all. Okay? All right. I'll see you next time.